Hello, students. This is the fourth lesson in Module 9. What I'd like to do is give you an overview and some strategy on some diagnostic tests to check model assumptions in the ANOVA. We'll also mention some alternatives when some of the assumptions are violated. So the objectives of this lesson are to check the ANOVA assumptions using a Shapiro-Wilk test and a Bruce-Pagan test. Then we also want to conduct alternatives to an ANOVA test when homoscedasticity or normality assumptions are violated. We began this module with the one-way ANOVA, and one of the ways to write the ANOVA model is like this. We had capital Yij is the jth root mean plus this epsilon ij, where the assumption here was that epsilon ij came from the normal distribution, mean zero, standard deviation sigma. We were, throughout this module, referring to this as random noise. But there are two important assumptions being made in this. First of all, that these epsilon ij's are independent and normally distributed. And secondly, that the variances are equal for each group, that this sigma, standard deviation, is the same for each group. This equal variance assumption is referred to as the homoscedasticity assumption in literature. Okay, so technically, before we use a one-way ANOVA, we should check these assumptions. And similarly for a two-way ANOVA, which I will show you in an example momentarily. So how can we check these? Well, let me take you back to something that we've learned already. In Module 8, Lesson 4, we discussed the Shapiro-Wilk test for normality. That test, the null hypothesis is that the data follow a normal distribution, and the alternative hypothesis was that the data do not follow a normal distribution. So to check this first model assumption of the ANOVA, we can use the Shapiro-Wilk test on the residuals. Now, for the second assumption of the ANOVA, I will take you back one module before that, which is Module 7. In Lesson 3, we learned an F-test for equal variances. In that test, the null hypothesis was that two variances are equal, and the alternative was that the two variances from two different populations are not equal. Well, we can use a generalization of this test called the Bruce and Pagan test on the residuals. The Bruce-Pagan test is in this LM test package. Okay, so far we know how to test if the model assumptions hold, but what do we do if they do not hold? Well, the first case, let's say it's only homoscedasticity that is violated. What that means is that the residuals are still normally distributed. Okay, so if we run our two tests, for the Shapiro-Wilk test, we will fail to reject H0. For the Bruce-Pagan test, we will reject its H0. So in this case, the situation is very similar to when we had a t-test with unequal variances. This null hypothesis of equal means in the G groups can be tested by a test proposed by Welsh. And in R, it's right here, this one-way dot test. Next, for case 2, we have the normality assumption is violated. And what this means is when we run a Shapiro-Wilk test for normality, we will reject H0. Now, we had a module on non-parametric tests, and if we learned anything in that module is when we do not have normality assumptions, which come from the parametric tests, the best choice is to use a non-parametric alternative. That's what we would do here. We have this Kruskal-Wallis test. This is a non-parametric test. And it's a generalization of the two-sample Wilcoxon test. It uses rank sums. And in R, we can use this Kruskal dot test. But one thing that we could also do, Another theme of our non-parametric testing module was the wonderful permutation test. So we can also conduct a permutation test version of the ANOVA. The benefits of the Kruskal-Wallis rank sum test and a permutation test is these are robust tests, and they are wonderful when we do not have the normality assumption. Before we end this video, I want to go back to R and show you this Shapiro-Wilk test and Bruch-Hagen test on an example we had in our last video. First, in order to use the Bruch-Hagen test, we need this LM test library. Now, one thing we looked at in the two-way ANOVA lecture, we looked at this tooth growth data. We used just the observations that had either 1 milligram per day vitamin C or 2 milligrams per day vitamin C. Our data was the tooth lengths. One of our factors was the type of supplement used, either ascorbic acid or orange juice. The other factor was the dose, which is either 1 milligram per day or 2 milligrams per day. Now, I used the ANOVA, two-way ANOVA, without testing anything. In fact, I showed both in our lecture. I showed the full two-way ANOVA with the interaction term, and then the two-way ANOVA without the interaction term. So just to illustrate the Shapiro-Wilk test and the Bruch-Hagen test, maybe I will just do this for the linear model without the interaction term. Here is the Shapiro-Wilk test. You noticed this is a large p-value, 0.3726. Okay, that looks good. I failed to reject the null, which means I cannot conclude the residues are not normally distributed. And then we have this Bruch-Hagen test. Once again, I have a very large p-value. I failed to reject its null hypothesis. I cannot conclude the data do not satisfy the homoscedasticity assumption. So based on these two tests, I could run the two-way ANOVA, in this case, without the interaction term. Okay, at this point, I have multiple Canvas pages for you to practice these diagnostic tests and also alternatives to the ANOVA when some of the assumptions are violated. Thank you so much, class.